So think back into the fall when we would hydrate triple bond. How did that go? We'd say, oh, it's in accordance with Makartnikov. So we might come up with something like this, and then imagine water eventually hitting there and get. So what do we call this thing? We called it an enol, and we had this fancy word called tautomerism, where it looks like that hydrogen comes over here. And we called this the enol. What did we call this? The ketone. We called it keto-enol tautomerization. And the reason why we might encounter this again today is we're going to deal with an alpha carbon that's right next to a carbonyl group. There's all this chemistry that can occur there, so I figured this would be a good refresher. So here's the enolate ion. This kind of looks like the keto form, but it's not an ion. But anyway, here's the enolate ion, and you've seen the enolate before. If we had a OH there, that's what we just saw. So an hydrogen adjacent to carbonyl carbon, we say is somewhat acidic. Base can pull that off. Now we have this nucleophile, and it can hit up with an electrophile. Alpha substitution is the substitution of one of the hydrogens attached to the alpha carbon for an electrophile. Alpha is adjacent to carbonyl carbon, and the reaction occurs through this enolate ion intermediate. And we can either imagine the lone pair of electrons going after the electrophile, or we can just imagine double bond electrons realizing it's going to add that carbon there. So that's what this hint is. You can show either form going after the electrophile. Condensation of an enolate with an aldehyde or ketone. Once we form this, so you've seen this with Grignards and organolithiums and the acetylide ion, we go all the way back to the fall, and then eventually we get this addition product. The enolate ion attacks the carbonyl group to form an alkoxide, and then the alkoxide gets protonated. Protonation of the alkoxide gives the addition product a beta hydroxy carbonyl compound, alpha beta hydroxy carbonyl compound. So we just saw there's quite a few carbonyl carbon species. Let's look at an ester. Same type of general thing, runs into there. But now instead of getting protonated and giving us a beta alcohol, the enolate adds the ester to form a tetrahedral intermediate. Elimination of the leaving group, alkoxide gives the substitution product a beta carbonyl compound. So the previous one gave us a beta hydroxy compound. This gives us a beta carbonyl compound. So here's what I warmed you up with before, not a chalk talk, but expo marker exposition. Here's the keto form. Here's the enol form. So the tautomerization, like if that hydrogen would go there and you get your carbonyl carbon back. And you can see equilibrium process favors this. Acetaldehyde here, or ethanol, a little better, but still favors the keto form. Tautomerization is an interconversion of isomers that occurs through the migration of a proton and the movement of a double bond. So if you remember back in the fall, we saw that this hydrogen doesn't move down here. It's typically a hydrogen in the solvent, but it doesn't really matter. And also don't confuse these with resonance forms. And of course you'll say, well, yeah, I know the definition of resonance forms. One resonant forms differ from another by only the movement of electrons. Electrons have moved, but we have an atom that's moved. So tautomers are not resonance forms. So it almost looks like we're gonna do what we did last at the beginning slide. A base can pull that hydrogen off. Here's the enolate ion. And so solvent, it wouldn't necessarily have to be this exact molecule, supplies a proton. And so here's the enol form, and here's the keto form. And I always want to call this the keto ion. I don't believe that's good. The enol form and the keto form. So hydrogens on alpha carbons are acidic, can be extracted to form a resonance stabilized enolate ion. Here's our enolate ion, and here it got protonated. The equilibrium favors the keto form over the enolate ion. That's this thing over this thing. All right, well, that was base catalyzed. Let's do the acid. So I've told you before that anything acid catalyzed with carbonyl carbon, we protonate the oxygen first. Oxygen's protonated, and then you can imagine those electrons jumping up, putting our carbocation there. What do carbocations do? They can eliminate hydrogen to form an alkene. So there's the enol form. In acid, proton transfer usually occurs by adding a proton in the new position, then deprotonating the old position. In base, proton transfer usually occurs by deprotonating the old position, then reprotonating at the new position. So we need to talk some stereochemistry. At one point, this was a mystery. I put my thumb out, carbonyl, I can go around it. This is R. Now all these are what we might say acidic or enolizable, acid or base. Pulls that off, we have our electrons. So here's the enol form, which has no chiral centers. Well, we just won't worry about that. We pulled off that proton there. Now when we go back to the keto form, it can come from, when we take some that's achiral, put that hydrogen back on there, we get both enantiomers. So it's something to be aware of. If you have some nice optically pure enantiomer there and you let it get around base or acid, pretty soon you can end up with a bottle of both enantiomers. For aldehydes and ketones, the ketone form is greatly favored at equilibrium. If a chiral carbon has an enolizable hydrogen, a trace of acid or base allows that carbon to invert its configuration with the enol serving as the intermediate, and this is called racemization. So it doesn't matter that equilibrium is way over there. If you have a little acid or base, small amount, and sits on the jar in a bottle on the shelf for a month, and all of a sudden you don't have your pure enantiomer anymore. pKa for the alpha hydrogen of an aldehyde or ketone is about 20. Much more acidic than the alkene or alkyne. So here's the alkane, greater than 40. Some books have it at 50, and the alkyne was around 25. Less acidic than water or an alcohol. Only a small amount of enolate ion is present in equilibrium. So if this was a hydrogen, it would be an aldehyde. We're looking at a ketone here. pK roughly 20. Alkoxide, its conjugate acid is alcohol. pK of 16 to 18. So anyway, that comes around, easily pulls off that hydrogen ion. But notice our equilibrium arrows. Then we form the enolate ion. We have a minor and major contributor. And equilibrium still lies to the left. So here, cyclohexone, ethoxide ion. We have values for all these. And here you see the enolate ion. And so this has a smaller pKa, so this is a stronger acid. And equilibrium favors the formation of the weaker acid. Wants to hang out over here. So what do we need? Needs stronger base. The equilibrium mixture contains only a small fraction of the deprotonated enolate form. Why do we need stronger base? Because we want to use this to do chemistry. Even though the keto-enol tautomerism equilibrium favors the keto form, addition of an electrophile shifts the equilibrium towards the formation of more enol. So these things being in equilibrium, in our energy diagram, we could come up with a delta G and turn it into an equilibrium constant. But if there's some electrophile around, it reacts. Now this is lower. So another reagent to learn and put on your note card for an exam, LDA, lithium diisopropylamine. So here is diisopropylamine, pKa of 40. Seems like a regular old alkane, but evidently I'd argue, this is where I'd make the argument that pKa for an alkane is closer to 50. So to pull one of these protons here, I have a pKa about 50. This one here, pKa of 40 according to the book. So N-butyl-lithium, how is it you want to visualize all organometallics? Probably this way. A lone pair on your carbon, you have a carboanion. That readily occurs. So yeah, we protonated this thing and formed butane. Seems like a waste of organometallic reagent, but now we have this nice strong base. LDA is made by using an alkylithium reagent. We probably get the cheapest one we can, probably butyl lithium, and we deprotonate diisopropylamine And DLA can be convert a carbonyl carbon compound into its enolate with equilibrium going all the way to the left. So here's our same example we just had. Now we got this powerful base, and now you can see this thing is an acid pK of 40. We'll call this thing an acid pK of 19. So equilibrium shifts way over here. So we put this in our flask, add this to the flask. What are we going to add next? Electrophile. We get this lithium salt of the enolate. We'll probably come back to LDA and doing synthesis later on in the chapter. Alpha halogenation of ketones. So here's a ketone. Here's that acidic proton, some base, a halogen, and now we have an alpha haloketone. The ketone is treated with a halogen and base, an alpha halogenation reaction occurs. The reaction is called base promoted rather than base catalyzed because a full equivalent of the base is consumed in the reaction. Remember, our definition for a catalyst is that it gets regenerated or it's not consumed in the reaction. And we can see we get water out of that hydroxide. It gets consumed. What's the mechanism? Alpha hydrogen gets abstracted by base, form water. Here's our enolate ion. Here's our electrophile. And so if we had sodium hydroxide here, we have sodium halide over here. Base promoted halogenation takes place by a nucleophilic attack of the enolate ion on the electrophilic halogen molecule. Let me just digress for a little bit. You know, I think of halogens as being electronegative. Well, when you got two of them here, remember back when London dispersion forces were explained, we say this electron cloud is polarizable and we get an instantaneous dipole and induced dipoles on other molecules. So we got this negative thing, and this thing has an electron cloud that's easily polarizable. When this gets close, all the electrons shift over here and this thing becomes positive, and that thing grabs a hold of it, and then those electrons leave. And like magic, the products are the halogenated ketone and a halide ion. Now this reaction was observed in various forms before it was ever understood. We can have multiple halogenations. So here we have one already has a halide on there. This comes by, there's our enolate ion. This happens again. Now we don't have any more alpha hydrogens. The alpha haloketone produced is more reactive than ketone because the enolate ion is stabilized by the electron withdrawing halogen. So this negative charge here through induction can be stabilized by the bromine atom. And so this occurs faster than the first one. Because the tendency for multiple halogenations, this base promoted halogenation is not widely used to prepare monohalogenated ketones, but it is used in this famous reaction called the haloform reaction. Haloform. What's the common name of this chemical species here? Trichloromethane. Nobody calls it by that. One of the earliest
anesthetic.
When you practice anesthesia, what do you use? Ether, laughing gas, chloroform. They all serve the same purpose. So we call this a methyl ketone because there's the ketone and just a methyl group. A methyl ketone reacts with a halogen under strongly basic conditions to give a carboxylate ion and a molecule of haloform. And so if this was chlorine, we'd get chloroform, and we could get bromoform. And this thing isn't. We'll look and see how the iodoform of this, when we use I2, we get this yellow precipitate, and it's a test for a methyl ketone.